Welcome back, everyone. Let me introduce today's speaker. It's Tomáš Bučko. He's an associate professor at the University of Bratislava. He's got an interest in VASP and has been contributing for almost 2 decades. His scientific interests lie in catalysis, and as a consequence, he has really become the pioneer of all molecular dynamics features in VASP. It's fantastic to see that all these advanced MD features now get to shine after they become computationally so much more accessible and feasible after training a MLFF. And I'm excited to hear about modeling chemical reactions in advanced MD methods in general from you, Tomáš, today. So take it away, MD approach to reaction kinetics.
Thank you, Chris. Hello and welcome, everyone. Today, I will talk about MD approach to chemical kinetics. At the beginning of the lecture, so we will discuss the basic workflow, and then we approach it at practical realization. So we will discuss how to make the choice of reaction coordinate and how to compute individual terms that we need to express activation free energy. Then we will talk a little bit about analysis of statistical errors, and in the end, we will make comparison of MD and static approach results. Just to remind you, we created a PDF document that contains the lecture material, and this material is available for you for free download. Before I really start, I would like to say that I assume that you have watched the static approach of reaction kinetics lecture and understand the basics of static approach. And this is important in particular because I'm going to use the notation and definitions that I introduced at the beginning of that lecture. I will also assume that you are familiar with the basics of molecular dynamics simulations. If this is not the case, you might want to check out our video on Introduction to Molecular Dynamics, which is on the VASP YouTube channel. On the previous lecture, we discussed this equation, this expression of free energy of activation that comes from transition state theory. Then making several quite crude approximations within static approach, we were able to compute this quantity or express this quantity in the terms which can be obtained just in relaxations and harmonic frequency calculations. So this so-called static approach is very effective and it's useful for rapid exploration of chemical reactions, but its accuracy is also quite limited, especially when applied to extended systems with non-trivial potential energy surfaces. So today we are going to discuss ab initio molecular dynamics approach to that, and we will abandon all these crude approximations made in the static approach. In particular, we will not assume any special potential energy surface topology. We will make no assumptions about the quality and the types of degrees of freedom we will deal with. And we will make no assumption about the quality of coupling between different degrees of freedom. Yeah, so in molecular dynamics, we employ ergodic hypothesis to express ensemble averages. So instead of explicitly computing averages over all configurations and phase space points, so we instead compute temporal averages. And all quantities that we need to compute activation free energy via this formula are one way or the other expressible as ensemble averages. So this will be the working formula for expressing all these terms here. In so-called ab initio molecular dynamics, the Hamiltonian that we use either here or to propagate equations of motion to generate this time evolution of system. So this Hamiltonian is based on the potential energy determined by solving Schrödinger equation. Okay. Still, we are using classical equations of motion, so as generator as propagator of the system. So that also means that the ensembles that we are producing in ab initio molecular dynamics are semi-classical ensembles. That also means that by these techniques, we are not able to take into account nuclear quantum effects such as zero-point vibrations or tunneling. Therefore, this method this is limitation of the method. It's not suitable for simulations at very low temperatures where these effects cannot be neglected. In the previous lecture, I suggested simple test to see how important quantum mechanical effects are. And this test consisted in comparison of static approach results employing quantum mechanical and semi-classical expressions for vibrational free energy. So we apply this test to our demonstration reaction, which is carbonylation of methyl group in zeolite. And we found that the difference between semi-classical and quantum mechanical static results was pretty small. It was only 12 millieV. So in terms of relative error, it is error of 1% only. This can be neglected because the statistical error we make even in very well converged molecular dynamics is at least of this order, but usually a little bit higher. So this systematic error is basically comparable to other sources of error which we have in molecular dynamics. So this can be well neglected. So that means that semi-classical expressions would work for us, and molecular dynamics, use of molecular dynamics is justified for our reaction at these particular conditions that we consider. This is my basic workflow that I use in my simulation. I will start with step 0, which it's not absolutely necessary to perform it, but I highly recommend it. I always start my simulations first by performing static approach calculations. This gives me first idea about the structures, about the path connecting stable states and transition states, and about the basic energetics. It's very useful to start with that, and it's relatively inexpensive compared to all steps that will follow. The real first step in my workflow, in molecular dynamics workflow, is to define approximation to reaction coordinate, which I call Xi here. This is extremely important step because this Xi so appears in all of these terms. Okay, so it's very important to make a reasonable choice, and that's why it is quite important before running any other calculations to make some sanity tests to check whether the choice that we made is really reasonable. So with that, we can then perform a straightforward molecular dynamics simulations that we use to obtain probability density. Then we determine, based on the results that we see, we determine some suitable reference reactant state and obtain the value for that. Then this is the most heavy part of calculation in terms of CPU time needed. That's calculation of reversible work. Next step is relatively cheap. We need to determine conditional average of absolute value of velocity. And with that, we have all the data needed to evaluate this equation. And finally, it is good practice, again, not absolutely necessary, but it is good practice also to evaluate the statistical error. The thing is that unlike in the static approach, in molecular dynamics, we are working with statistical data. All the results are obtained as ensemble averages, which of course are determined only up to some uncertainty, right? And we can design our simulation protocol in such a way as to reach certain precision. That means as to obtain a result with uncertainty smaller than certain threshold. Okay, so this is good practice, and this is something I will talk about a little bit at the end of this talk. So the first task is to choose a reaction coordinate. I can't emphasize enough how important step this is. If you make mistake here in this step, everything that you compute using that will be wrong. Okay, so the suitable Xi, approximation to reaction coordinate, must be a continuous function of atomic positions and should be chosen such that it changes monotonically throughout the transformation. This is important because you must be able to monitor the progress of reaction just by checking the value of Xi. Infinitesimally slow change of Xi from the initial to final state must be a reversible process. That means that if we compute free energy for the transformation between any two states on the transformation path, the result that we get when we move from state 1 to state 2 must be identical up to the sign to the result that we obtain when we move in other direction. Okay, so this reversibility condition is very important. There are more criteria. If you are interested in more details about is concerning this problem, I would recommend you to read the paper by Baron Peters here. Let's come to our demo reaction. Here, the distance between carbon-oxygen is broken during reaction and the distance between carbon-carbon is created. So obviously, these 2 degrees of freedom should be somehow involved in definition of reaction coordinate. Okay, so the usual choice for this kind of substitution reaction is just distance difference between 2 distances, R1 and R2. So let's use this coordinate also for our case. Now we need to define this coordinate. We need to define the input file called iconst. And so in VASP, we can define 2 classes of coordinates. So one class are so-called primitive coordinates, which explicitly depend on atomic positions. And the other class are complex coordinates, which explicitly depend on primitive coordinates. So looking at our candidate reaction coordinate, you see, so it's defined via distances R1 and R2. Each distance is defined via atomic positions of atoms involved. So R1 and R2 are primitive coordinates, but in Xi, these primitive coordinates are combined together. So Xi is of this type. It's a complex coordinate. So now the format of iconst file is as follows. Each line defines 1 coordinate, primitive or complex. If you have a complex coordinate in your definition, you always have to start with primitive coordinates that define the complex one. Okay, so this is also our case. So the first line defines the distance R1. So this is distance between atoms 3 and 25. Okay, and an R means that this is distance. And the last integer here, this is the status. I will comment on that in a minute. So the second line defines the second primitive coordinate between atoms 3 and 2. And the final line, this is the complex coordinate, which now combines the 2 primitive coordinates defined above. Now, what kind of complex coordinates do we have? S means weighted sum. Okay, and the 2 numbers that follow are the weights associated with the first and the second primitive coordinate. So first coordinate is R1, its weight in the sum is -1. So this is this number. And the other primitive coordinates are 2. The weight associated with it is +1. So that's why I have +1 here. And the last number, again, that's the status by which we tell VASP what to do with the coordinate. And the 0 is the code for constraining the value of coordinate. Constraint itself could be time dependent. Nevertheless, 0 means we are constraining it. Another useful setting that we shall make use of is 7. That means monitor coordinate. We will come back to that. One important thing I should mention, once you define complex coordinate, then the primitive coordinates are only used as a basis for complex coordinate definitions, and therefore the status is irrelevant but must be defined. So in our case, we defined 3 coordinates, but in reality, since we have complex coordinate here, these 2 are only used for definition of complex coordinate, but they are not constrained by themselves. Okay, they are not constrained. Okay, now having made our choice for Xi, it makes sense to spend some time, invest some energy into testing and into some basic validity check. So I will show you 3 sanity tests I'm routinely doing for my reactions. The first one is very simple, and I here make use of my data from static calculations. Here I simply check whether Xi varies monotonically and continuously along the intrinsic reaction coordinate from static calculations. So in other words, all I do is I simply monitor the value of Xi using the structures defined in the XDATCAR file generated by IRC kind of calculation. So this is how I do this. So imagine that my 2 calculations for negative and positive branch of IRC are organized subdirectories M and P. So here I have XDATCAR and outcar file. So then I use this utility to read structures from XDATCAR and compute the value of coordinate defined in the iconst file. Okay, and I store it in the file xi dot. Then I do the same for the positive branch. By the way, all the utilities I'm going to mention will be available for you to download. So by that, I collect the Xi values for negative and positive branch of intrinsic reaction coordinate. Then I extract information on the sign path, length from the VASP output. And yeah, so I store them in files chi.dat. And in the last step, I paste. So these are 1-column data. Here I create 2-column data out of them. And here I just sort by the length taken along IRC in ascending order and generate this file, which can then be visualized. Now we see that starting from the reactant, which, so the xi, which is on y-axis, takes value -1.7. And as we move on through the reaction, so at transition state, the value of xi is close to 0. And as we move on towards product, we reach it at the value around 1.5. So we see that this transformation, so the dependence of xi on chi is monotonous, it's a continuous function. There is small exception. There might be small oscillation at the beginning, at the end of IRC trajectory. That's okay, because at this stage, the reaction is already over. So what we typically observe that we are close to minimum and molecule just reorient itself a little bit with respect to substrate, for instance. So these small oscillations could be ignored. What is really important that in the central part where the actual chemical reaction takes place, here the function must be monotonous. Another quick test that I make and utilize the static approach result is the one where I check if the motion of xi is parallel with the Hesse matrix eigenvector corresponding to the unstable direction in the relaxed transition state. Okay, so all I need here is the outcar file from vibrational analysis and the definition of xi in iconst file format. Okay, so technically what we do, we make a transformation of Hesse matrix, and this transformation involves Wilson's B matrix, which is Schmidt orthogonalized with respect to constraint degree of freedom. Okay, and then this kind of Hesse matrix is used in vibrational calculation. So by that means we effectively remove the constraint degree of freedom from vibrational calculation. That is implemented in the program VIPFRAC. Okay, so all that is needed really is the outcar file and iconst file defining the constraint. And here I compare the output from VIPFRAC, so the part of frequency spectrum obtained for an unconstrained system. This is transition state. So I have 1 imaginary and 3 vanishing frequencies. And this is the same for the constraint system. So here you see the program detected the constraint, but the imaginary frequency that was originally there now vanished. So I have just 4 vanishing frequencies. This is the effect on the overall vibrational spectrum. This is vibrational density of states. So in this notation, negative numbers correspond to imaginary frequency. So yeah, this disappeared, and the rest of spectrum is affected only little. Okay, so from that, we see that at least in transition state, xi is indeed parallel with the intrinsic reaction coordinate. Of course, this kind of test is only relevant, only makes sense if the temperature or entropic effect do not cause a significant change in mechanism. Okay, in that case, of course, you don't expect that low temperature transition state would be of any relevance. And my final test is also the complex one. Okay, it has several stages. So in this test, I perform molecular dynamics simulation in which I change the value of xi continuously throughout the simulation. So I call this kind of simulation slow growth, MD. This can be achieved by, of course, defining the iconst file where the coordinate of interest has status 0. And the incar file contains the usual flags for molecular dynamics. So this is Iberion 0 activates molecular dynamics. This defines number of steps. Time step in femtosecond used in integration of equations of motion. And this is temperature and thermostat related setting. And the rate at which I change the value of xi every single step is defined by a flag called increm. Okay, so at every step I change increm by this amount. And for the purposes which will be obvious in a minute, let's define also this extra flag, which is L blue out true. I perform this slow growth simulation of total length of 10,000 steps. I don't like to generate large output files, so I usually organize my simulation such that I split them into shorter sequences of typically of 1,000 steps. So this calculation was performed as 10 sequences. I selected my transformation rate. so that starting from relaxed reactant, for which I obtained Xi minus 1.7, in 10,000 steps, I crossed transition state and moved a bit further behind it. Okay, so with this setting, I reached this state, which is well behind expected transition state, expected based on static approach result, which is close to 0. Now, this is how I perform the calculation. So here I define the command which runs VASP. Then I iterate over MD sequences. I have 10 sequences here. At the beginning of each sequence, I just save the postcard file, run VASP. And when this is finished, then I store the most important output files here, report and x.car file. And finally, I copy contcar file to postcar so that the next sequence starts exactly where the previous one ended. Yeah, as a side remark, the postcard files that we generate in this way, you see, so this sequence generated postcard 1, 2, 3, up to 10. So they have this property that the structures represented by these postcard files differ in value of Xi, differ by a constant value of Xi, which is in this case rate by 1,000 steps, that's 0.2 angstrom. So you see the slow growth simulation can be used not only for the sanity test we are discussing right now, but also as a tool to conveniently prepare configurations with some well-defined structural parameters. And this is the feature we are also going to make use of, because the postcard files we are generating here will be then used in our Blue Moon ensemble calculations we are going to discuss soon. Okay, so imagine the slow growth simulation is over. Now we would like to check whether the atomic motions in the trajectory within this generated by slow growth, whether these atomic motions really correspond to expected structural changes for the given reaction. Okay, so we would like to visualize trajectory we generated. So for that, I use this sequence of bash commands. So I loop over molecular dynamic sequences, test if x.car point integer exists, and if it does, I convert it to XYZ format, which can be visualized by common visualization software such as Molde and JMol, Vesta, and other software. So for that, I'm using this conversion utility, and here I used 10 as argument, which tells the program to select not every, but every 10th structure, so that my animation that I'm creating is not too long. I can watch it quite quickly. All right, so this can then be visualized. So this is our slow growth, quite accelerated, and we just see as carbon monoxide approaches a methyl group at some point, carbon oxygen bond cracks, we got past the transition state. So this pretty much, nothing strange happened. This pretty much corresponds to what we expected. Yeah, so I think this test was successful. So next thing we should test using the same data we already generated is whether such transformation is continuous. To this end, we will use data available in the report file. So for any coordinate with status 0, report file contains this kind of output information. So for every n-blocked molecular dynamic step, n-block by default is set to 1. So if you use default value, so then for every MD step, you will see a line like that in the report file, and it contains the desired value of reaction coordinate, or the coordinate with status 0, the actual value, and the difference between those two. So this is one type of useful output. Another useful output we shall need is the Lagrange multiplier used in the shake algorithm to impose the constraint. And this Lagrange multiplier plays the role of restoring force needed to constrain Xi. So the idea is to simply explore how this Lagrange multiplier lambda changes as a function of Xi. And we would like to see it's a continuous function of Xi. And to have this output in the report file, that's why we needed to set lblue out true in the incar file. Okay, so this flag actually activates this kind of output. So here is how I extract lambda versus Xi dependence. Again, I iterate over all MD sequences. And for existing report file, I first extract the value of reaction coordinate and store it in a first temporary file as one column in one column format. Then I extract a Lagrange multiplier, store it in the second temporary file, and I merge these two pieces together to create two-column file with two-column format, which is called grad.dat, which we can then expect. Okay, so first of all, the profile that we obtain, lambda versus xi, should be a continuous function. So lambda should be a continuous function of xi should the transformation be reversible, of course, right? I intentionally start with a bet behavior example. If you see something like that the forces increase and suddenly something cracks and we change even the sign from large positive to large negative, this is discontinuity. This is how it looks like. And this is a very clear indication that the process is not reversible, which usually means that your xi is not suitable, right? Or some bireaction, side reaction took place. Fortunately, nothing like that happened in our case. So the lambda versus xi dependence is noisy, but nevertheless, it's free of any obvious discontinuity. So that's fine. This is how it should look like. Now we started in reactant state and we achieved some state after transition state. Now what we can do is basically do the things other way around. So we start from the final state and move back to our initial state. Okay, so for that, we need to copy cont car we generated at the end of forward, a slow growth to cont car, and we need to change sign of increm from positive to negative number. Okay, so then I repeat, I again run slow growth 10,000 step. I can again visualize what happened. It was not very much interesting. It was pretty much the same as we've seen before. And I can again extract lambda versus xi dependence. And I compare my result with the result for the other transformation direction. Here we are. And as you can see, these two profiles are qualitatively similar, as they should be if the process is reversible. It must be independent of the transformation direction. Fine. So now our candidate reaction coordinate passed all sanity tests. Now we can start using it to produce something useful. So the first task is really to determine a probability density and choose the reference state. So formally, probability density is defined as ensemble average, with Dirac's delta function being phase space function associated with that. Practically, in molecular dynamics, what we need to do to compute this is to run sufficiently long, straightforward molecular dynamics for the reactant state and monitor the values of xi. So for every step or for sufficiently large sample of configurations that we generate, we would like to collect values of xi. This can be achieved as follows. So we use the same iconst file as in our slow growth simulation, but we need to change the status from 0 to 7, by which we tell the program to monitor the coordinate rather than to constrain it. Okay, with status 7 setting, all VASP does is just prints the value of the coordinate in the report file, but it doesn't manipulate the coordinate or the system in any other way. Okay, so nothing special needs to be defined in the incar file. This is just the common molecular dynamics setting, the same as we used in previous calculations. So the first step, so first thing that we need to do is really to monitor and obtain values of xi for a representative sample of reactant configurations. Okay, and then we need to use some representation of probability density, and in the end to choose suitable reference reactant state and evaluate the probability density function. I forgot to say, if we monitor some reaction coordinates, so for every coordinate with status 7, the output that we see in the report looks like this. So for every n-blocked step, we have one string introduced by MC, and which contains the value of xi in this case, or for monitored coordinate in general for the current molecular dynamics step. Okay, so let me mention briefly or say something briefly about a histogram approximation that we can use to represent or to estimate probability density. So in this method, the interval defined by minimum and maximum value of monitored coordinate xi is divided into several regular intervals. So in my example here, this is my minimal value, this is maximal value, and I defined 6 regular interval of width delta psi. Okay, so the black points here represent measurements or the data that I could see in molecular dynamics, and this is just small fragments out of all data. Okay, so in histogram approximation, so what I do, I simply count how many measurements fall into each of these intervals. Okay, so I have no measurement in the first interval, so I mark 0 here. I have 2 measurements in the second interval, mark 2, 1 measurement here, 3 measurements here, etc. And then I need to normalize the result properly. So of course I need to divide by number of measurements so that the sum of all columns is unity. And then I need to divide by the width of bins, so that when I integrate the resulting function, it's properly normalized. So the integral should be 1. Now the number of bins, that's a free parameter of method. So it's up to you as user to set it. Okay, and optimally it should be chosen as a compromise between 2 conflicting criteria. So first, if the number of bins is too large, no, if it is too small, then the interval, so the width of bins is large and might be larger than desired resolution. So by selecting too small number of bins, we lose resolution. The other extreme is when we choose too large number of bins. In that case, number of measurements falling into each of these interval will be always small, leading to large statistical uncertainty. Okay, and meaning that again, probability density will be too noisy and it would be difficult to accurately read the value for any psi that we select. So optimally, it should be a relatively smooth function which contains all the important details we are interested in. Alternative to histogram approximation, and this is my preferred technique, is kernel density estimation. I'm using Gaussian kernels with that. So in this method, the probability density is expressed as a sum of normalized Gaussian shaped functions. So again, let me illustrate it on example. So this is again the same fragments of data, say from molecular dynamics. This is on y-axis, I have the value of psi. And now, instead of dividing this into some regular intervals, I do something else. For each point, for the value of each point, I placed a Gaussian on it. Okay, so let's say the first point was centered at, I don't know, this is perhaps 2.6. So I placed the Gaussian at the point 2.6. This point is at 3.4, so I placed Gaussian there. I have 7 data points here, so I have 7 Gaussians here, right? So, and then I sum up the result, normalize it properly. So every Gaussian function contributes by 1 to total area. So I need to divide by number of Gaussian, and then I get approximation or estimation of probability density. There is also one parameter in this method. This is sigma. By that you control width of Gaussians, and it's called smoothing parameter or bandwidth. And it needs to be defined by user, and you should set it again as a compromise between 2 things. The too large value leads to over smoothing, you lose details, and too small value again leads to large uncertainty in results. So it would be difficult to read the value. So it's not smoothened enough, let's say. Smoothing is not sufficient. So optimally, it should look like that. And to find the optimal value, it's usually not very difficult, but as a good starting point, you can use some empirical rules available in literature, for instance, that by Scott. Okay, so this is what I did. So I performed quite long MD simulation to accumulate sufficiently rich data. So the total length of my simulation was 200,000 steps. Again, I split this into 200 sequences. I monitored the value of a reaction coordinate and stored the resulting values in the file called mc.dat. This is how I did it in practice. So here again, I iterated over MD sequences for existing report files. I filtered out line containing string MC and picked a third entry, and that number was then stored in the MC file. Afterwards, I post-processed that. I used kernel density approximation with this smoothing parameter, and the resulting sum of Gaussians was then rendered onto a grid of 100 regularly distributed points. Okay, so I realized that with utility called normalized KDE, which takes the name of file with data, a smoothing parameter, and number of grid points as arguments. So here is the result. So the red line here corresponds to KDE. Blue, this is histogram approximation. You see qualitatively the results are the same. Now the next task is to select suitable reference reactant state. As we discussed in the previous lecture, this choice could be made arbitrary. Our result must be invariant with respect to this choice. Nevertheless, one should take into account that, as we shall discuss later, the standard error of activation free energy is inversely proportional to probability density in the reference state. So it is reasonable, it's a good strategy to select the reference point such as to maximize probability density, so something close to the maximum of probability distribution function. On the other hand, to facilitate analysis of differences between static and molecular dynamics results, it might be also reasonable to make the alternative choice to select simply reference value that corresponds to the value found in the static approach. Okay, so in most of my results I'm going to show you, I made this choice. So this corresponds to static result, but in the end I will show you also the results obtained using alternative choice. Okay, so having decided about the reference state, we just read off the value of probability density at that point. This is for one reference point, this is for its alternative. Now you could notice here that the structure of a reference reactant state in a static approach is very different from what we see in molecular dynamics. So in molecular dynamics, we generated structures that majority of them is very different from the potential energy minimum. Okay, so why is that? The thing is that in static approach, 0K, actually, so what we created is this kind of adsorption complex where carbon monoxide interacts with methyl group. But this interaction is weak. It's not strong enough to stabilize that system at a relatively high simulation temperature that we used. And during the simulation, carbon monoxide simply flies away. I visualize this effect here on these two pictures. So here I collected positions and orientation of carbon monoxide molecules from my molecular dynamics and put them onto one single picture. Right? So from that you have idea how carbon monoxide moved throughout the simulation. So here I did it for my DFT molecular dynamics, and here I did the same for purely harmonic system. Okay, so this picture corresponds pretty much what we assume in static approximation. And now you see that the differences are both qualitative and quantitative, because qualitatively you see that in the static or in harmonic picture, carbon monoxide never reorient itself. It's always oriented towards methyl group via its carbon end. Okay, whereas in fully interacting picture, carbon monoxide can easily change its orientation. Okay, in harmonic approximation, of course, this is just motion around the central value. So all we see is just slight horizontal and vertical motion, or translational motion of carbon monoxide, more or less. In fully interacting picture, this is very different because carbon monoxide can fly away, right? So qualitatively, we would expect that entropy of fully interacting reactant state would be higher than entropy of its harmonic counterpart. Higher entropy means lower free energy. And if nothing special happens with transition state, so lowering free energy of reactant should lead to increase in free energy of activation. So let's see about that. Okay, let's see about it later. Having decided about reference reactant state, we are at position to compute reversible work. This is the most difficult part of calculations. This is because we cannot use the standard molecular dynamics. Why? Because probability density of states in the transition regions for typical chemical reaction is orders of magnitude smaller than that for reactant state. That means that in order to be able to sample transition state, we would need astronomically long simulation time. Okay, so this is something we cannot do practically. Even in theory, it could be done. Okay, so that's why we need some specialized techniques specifically designed to tackle this problem. VASP implements several state-of-the-art methods. If you are interested in what's available, so please watch this video on VASP YouTube channel. So here within this lecture, I will exclusively focus on the use of a method called Blue Moon Ensemble technique. And I selected it, it's my favorite, because it's uncomplicated in terms of execution and post-processing. And unlike metadynamics, for instance, allows for easy statistical error estimation, and it doesn't hide anything. So if some problem appears, for instance, with definition of reaction coordinate or something like, or bireactions, so we will immediately see that from results. So in Blue Moon Ensemble approach, we compute free energy gradients in a series of constrained molecular dynamics simulations. So constraints are implemented via Shake algorithm. And in Shake algorithm, when we fix the value of psi, we at the same time actually also fix the value of associated velocity, and we fix it at 0. So this generates different kinds of ensembles, which are here distinguished from conditional averages using this label, constraint averages. Okay, and it's shown, it was shown by authors of the method, actually by these authors, that free energy gradients can be expressed in terms of these constraint averages. Here, lambda is the Lagrange multiplier used in Shake algorithm, the same as we used in slow growth simulation. And Z, that's the inverse of mass metric tensor associated with coordinate psi. Okay, so now having free energy gradients, then we integrate them over the path connecting the initial and final state, and this is how we compute the reversible work. In practice, we need to compute the gradients for several integration points with different values of psi, and the integration points should be chosen such that the integration interval is fully included in the interval delimited by integration points. So each such gradient calculation requires one separate constraint MD run. Okay, so having that, then we choose some suitable numerical scheme, for instance, Simpson scheme, which usually casts the integral into the form of a weighted sum. And this is how we then compute the reversible work. Now, you might have noticed that while the reference reactant value for reaction coordinate is selected by us, so we know what this value is, we don't know before these simulations, we don't know the position of finite temperature transition state, right? Fortunately, this is not a big complication, because what we do technically, we simply print what I call free energy profile. Free energy is function, reversible work is function of psi, and we determine the position of transition state as the point on top of that profile, on top of maximum. So it's a point of the maximum of such profile, or equivalently, we can also identify it from gradients. Stationary points should be the point where gradients vanish. So to run Blue Moon ensemble calculations, so these are just constraint simulations, we need to define iconst with coordinate with the status set to 0, just like in slow growth simulation. In the incar file, we should include line L blue out equals true, so that we obtain the output that we need to evaluate free energy gradients. Now, how to do that? So as we already discussed, for every n-blocked molecular dynamics step, we will see such line in the report file. And now you see the free energy gradient is computed as ratio between two ensemble averages, right? So the first average can be obtained by averaging the numbers that are written in the last column of such line. So last entry here. Okay, and the term that we average in the denominator, this is the second numerical entry in that line. So what we need to do is really to extract the last entry, make average of it, we get the numerator, extract the second numerical entry, average over that, and we get denominator, and that's pretty much it. Again, since we use status 0 for our coordinates, so we will see this kind of output in report file, using which we can check the value of a constraint coordinate at every single empty step. And the quality of this constraint depends on the tolerance factor used by shake algorithm. This is something you can control via shake toll parameter. By default, it is 10 to minus 5. Okay, so assume that we already performed constraint molecular dynamics for one integration point. Now we collect useful information. So here I iterate over the sequences that I produced. If a report point number exists, I just extract the line starting with b_m string and store it in a temporary file. After this loop is completed, then I extract the value of a reaction coordinate. It is constant throughout the runs. I only need to take the first number that I see in the very first file, for instance. Then I calculate the denominator, call it z, and for that I use this temporary file and I make average over entry 3. Here it is. Then I do the similar thing with the denominator. So I again use temporary file, make average over entry 5, and then I divide average by denominator by z, and I get directly the gradient for the point, and I print it. So it's gradient versus integration point, right? Then we need, of course, to repeat this procedure for every single integration point that we are using. So now, once again, once we plot gradient as a function of psi, we don't want to see any discontinuities. As before, discontinuity just means your psi simply doesn't work, or bireaction took place. In either case, you need to do something about that. You need to make new choice of reaction coordinate or introduce some bias potential to avoid side reaction. And that unfortunately also means that all the data that you produce up to this point could be thrown out, and you must start over. Fortunately, this didn't happen in our case, right? So our profile looks quite smooth. To generate it, I used 10 integration points distributed over the interval starting at relaxed, reactant, and 1 point just behind the transition state, this one. And now I initialized each constraint molecular dynamics simulation from the postcard file generated in the forward slow growth simulation that we performed within our sanity tests, right? So I utilized the data generated there. Now, the length of each constraint molecular dynamics run was 100,000 steps, right? So it's quite, so altogether I generated million structures. So this is why it is quite heavy calculation. Now, to represent the points on interval between integration points, I used cubic splines. This is this red curve that you see here. And with that, I was able to identify the transition state. That is simply the point close to 0. I had this information from static approach that I can expect transition state somewhere close to 0. And I identified a precise position of finite temperature transition state as the point where gradients vanish. So that's exactly that point here. Yeah, so the point that I identified, the finite temperature, yeah, psi takes this value in transition state. In static transition state, it was this value. Sign is different, but numerically, it's very similar. So we see that unlike in the case of reactant, the structure of finite temperature and, yes, so to say, static approach transition state is not very different. And this can be understood. This can be understood because when we impose constraint and we demand that the psi is close to 0, that also means that carbon-carbon distance and carbon-oxygen distance must be about the same throughout the simulation. Now, whenever carbon monoxide tries to leave transition state, as it could easily do in reactant, at the same time, we need to then elongate also this distance that moves, that also means that we would need to move positively charged methyl group away from negatively charged zeolite framework, right? So we would have charge separation, and that costs, right? This is unfavorable, and this is something that prevents carbon monoxide and methyl group to fly away, right? Okay, so now using free energy gradients, we can now integrate them. I use Simpson's formula. I obtained a free energy profile. And again, I represented the points between integration points by cubic splines, and I determined the reversible work needed to shift value of psi from reference reactant to transition state value as the difference between this free energy on top of this profile and free energy at the beginning of this profile. And this is the number that I obtained. And the last ingredient that we need for our to eventually obtain activation free energy is this conditional average of absolute value of velocity. It can be shown that for canonical ensemble, this conditional average can be obtained using this formula. So where conditional average of root square of inverse of mass metric tensor is involved. And this is exactly the same ingredient that we used in our constraint molecular dynamics calculations to express free energy gradients, right? So that also means that we have everything that we need to determine this quantity. Of course, we have to keep in mind that in constraint molecular dynamics, we actually produced constraint averages, but there is clear relation between conditional and constraint averages, which we can employ. So using it, substituting this expression to this formula, we can, after some manipulation, we arrive at this formula, which is now expressed in terms of constraint averages. Okay, and we just utilize the data that we already have from constraint molecular dynamics. So in terms of post-processing, it is almost identical to what we did when we extracted free energy gradients. So I'm not going to comment on that. This is basically the same thing. And here I plot this constraint average as a function of psi. So now we need to determine this constraint average for one specific point corresponding to the transition state. Obviously, unfortunately, it doesn't coincide with any of our integration points, but fortunately, as you can see, this function is a smooth function, slowly varying function of psi. So we can very reasonably well estimate the value of the conditional average for transition state just by interpolation. For that, we can use cubic splines, for instance. So this is what I did, and this is the numerical value that I obtained, and plugging it into the formula for average energy, I obtained this result. Now, before we put things together to finally evaluate our quantity of interest, I think now it's time to talk a little bit about the statistical error. This is the part of error that can be reduced, even though never fully eliminated, by just producing more data, in our specific case, running longer simulations, right? Now, in general, for a property X that is estimated as an average over NM statistically independent measurements, right? So the confidence interval reflecting the statistical uncertainty we are interested in is given by this equation, where Z epsilon X, this is called margin of error, and epsilon X, this is the standard error, and Z, that's quantile, whose value depends on our particular choice of confidence level. So for instance, Z is 1 if we choose 67% confidence interval level, or 1.96 if we choose 95% confidence level, right? So what we want to evaluate is actually this margin of error, which reflects uncertainty in our data. Now, what to do in situation that the quantity of interest is not directly the measured quantity, but it's rather the function of measured quantity. So let's say we are interested in quantity G, which is some function of another quantity X, which we measured and which we estimated as some ensemble average. Okay, by error propagation formula, here it is, the standard errors of the two quantities are related, where the proportionality factor depends on derivative of G with respect to X at the point corresponding to the average value, right? Now, this can be generalized to the case of two variables, or to the function which depends on two measured quantities, X and Y. In that case, the error propagation formula gets a little bit more complicated because, of course, in that case, a standard error related to X and Y came into the play, but there is also contribution from one additional term that is related to covariance between data X and data Y. So for fully independent data, the covariance is 0, right? And of course, the partial derivatives of our function with respect to X and Y are involved in this equation. And this can be then easily generalized to the case of function with more than 2 variables, okay? And this is the basis for our statistical uncertainty estimates in molecular dynamics. So in our specific case, our quantity G, so to say, so the main quantity now depends on multiple things. So first of all, so this reversible work is in itself computed as weighted sum, whereby each gradient for each integration point will contribute to the statistical uncertainty. And then, of course, we will have contribution from velocity and from probability density terms. So when you do the algebra, when you evaluate this using the error propagation formula, you should arrive at expression like that. So where I used shorthand notation, indicated here. And you see that specifically in the case of velocity and probability density, so it is the relative error rather than absolute error that matters for the total uncertainty in free energy of activation. So now what we should discuss now, how to evaluate the standard error linked with these individual components. Okay, so let's start with free energy gradients. They are expressed as ratio between 2 statistical averages. So again, we need to apply error propagation formula. Again, I introduced some shorthand notation. P is numerator and average in numerator, and Q is average in denominator. And this is the formula that I obtain using error propagation formula. It's important to take into account also this covariance related term, because obviously the terms in numerator and denominator are computed for the same set of structures, and these are all position dependent properties. So they are certainly to some extent correlated via their explicit dependence on positions. So when you use the same data, you can expect certain correlation. So you must not ignore this covariance term. Nevertheless, so with this formula, the calculation of standard error for each integration point is pretty straightforward. We just use the same data as we used to compute the averages. Only thing we have to be careful about is time correlation. That's something we shall discuss shortly. The next term is conditional average of velocity. This is simple because we have only average of one quantity here. So again, using error propagation formula, we arrive at this simple expression where R is shorthand notation for this constraint average. Again, after eliminating the time correlation, the calculation of this relative error is pretty straightforward. And finally, we have uncertainty contribution from probability density. Here, when we use kernel density approximation, one can show that the relative error can be expressed like this. Here, y, that's the probability density at the reference point. Sigma, that was our smoothing parameter. Mu, that's the constant which depends only on the choice of kernel function. For normal kernel, it is just 1 over root square of 4 pi. And n over L, this is our estimate of the number of uncorrelated data, right? We made our estimate using n xi correlated data, and imagine that L data in row are significantly correlated. So n over L is our estimate of uncorrelated data points. So that should be applied. Similarly, for histogram approximation, we have this expression for a relative error. It has similar form, just instead of sigma over mu, here we have the width of a bin in the histogram. Okay, and notice now that in both cases, KDE or histogram approximation, we see that the relative error is inversely proportional to the probability density at that given point. So the higher the probability density, the lower the relative error, and therefore the lower contribution to standard error of the final quantity, activation free energy. And this is the reason why it is a good idea to select the reference reactant state to be close to maximum of probability density. Now, all the formulas that we used in error analysis assume that our measurements are statistically independent, but of course, molecular dynamics produces strongly time-correlated data. An elegant way how to deal with this problem is log averaging method of Lieberg and Petersen. Here, starting from the full data, possibly correlated, we estimate the standard error using the usual formula. But then we start blocking the data. That is, we replace pairs of data points by their averages. Okay, so having block size 2, so we replace this pair by this average, and we repeat this. So by that, we reduce the number of data points by factor 2, but at the same time, we also increase the effective distance between two data points, because the effective distance in the original data was just 1 time step, and here it is effectively 2 time steps. Okay, and again, we compute our estimate of standard error, and we keep on blocking like that. So when we use this data again to block them, we again reduce the number of data points by a factor of 2. So altogether, this is the same result as if we blocked over 4 pieces of data here, right? And again, we compute standard error. So in the end, so we keep on doing this, so this blocking. In the end, we plot the estimated standard error as function of block size. Okay, and what we should see is that after initial steep increase, we should arrive at this plateau, and this gives us our best estimate for the standard error, and the corresponding point on the x-axis would be the length of correlated data, so the effective separation between uncorrelated data, to be more precise. All right, so imagine we have done that, we computed all the ingredients we needed, so now we can put them together and obtain the result. So here it is. This is my molecular dynamics result for activation free energy. This is the statistical error that I computed, assuming 95% confidence interval. Now, how does it compare with alternative choice of reference reactant state, Xi prime? Okay, so here we are. So we see some repartitioning of individual contributions. So we see that, for instance, reversible work is 50 millieV higher than before. And at the same time, of course, probability density is significantly higher than in the previous case. Okay, but when we put things together, we arrive pretty much at the same result, certainly within the statistical error, the same result as with the other choice of reference state. And this is how it should be. Our result must be invariant with respect to reference reactant state. And finally, let me make comparison of this result with our static approach result. So here I make the comparison with the semi-classical variant of static approach. So we see that the difference between the two methods is 0.12 EV, which is first of all well above the estimated error. It's 0.016, so it's order of magnitude larger than that. So this difference is statistically significant, so cannot be explained by insufficiently converged molecular dynamics. Okay. A second interesting thing is that the anharmonicity, that is the difference between MD and static, is almost as large as the contribution of vibrational degrees of freedom in static approach. That is, anharmonicity is as important as the harmonic contribution to vibrational free energy. Okay, and this really calls for some explanation. Why is that? Okay, so what we can do now is really to look at equation for activation free energy, look at each term, and make comparison one by one comparison between molecular dynamics and static approach. So let's start with reversible work. We have the MD result, and we can easily obtain the static result simply by constraining the value of reaction coordinate in our vibrational analysis, and using the vibrational spectrum of constraint system, of constant reactant and transition state in free energy calculation. Okay, so using that, I obtained this value for reversible work, which is just 36 millieV lower than molecular dynamics counterpart, but the total difference was factor 4 larger. So this doesn't explain. This is just small contribution to this difference. Certainly doesn't explain it. By the way, we can understand why this number is relatively small. This comes from cancellation in similar anharmonicities for transition and reference reactant state. One should keep in mind that reference reactant state is not exactly the same thing as free reactant, right? Because of presence of constraint, just like in transition state, carbon monoxide cannot really leave far away from methyl group. So even though there is some quantitative difference between reactant and transition state, it is not as spectacular as the difference between unconstrained reactant and anything else, right? So the next term to look at is the conditional average of velocity. Now, so this is the formula we used in molecular dynamics. In static approach, we use the same formula, but we replace the average of inverse mass metric tensor by a single value computed for the relaxed transition state. Doing so, I obtain this value, which is practically identical to what I got from molecular dynamics. So the contribution to free energy activation difference estimated using this formula is pretty much zero. It's negligible. That also means that the main contribution to the difference between the two approaches must come from probability density, which should not be surprising in light of discussion we had when talking about probability densities, right? So, but now let's try to quantify this effect. For that, we can use analytical expression for harmonic probability density. So to evaluate this, we need the force constant, kappa, associated with reaction coordinate. We can determine it by running constrained static, so constrained relaxations for several states close to minimum. Okay, then I fit my energy versus psi dependence, and from the harmonic fit, I obtain kappa as fitting parameter. Okay, so doing so, I obtain distribution like that, of course, Gaussian shaped, centered at our reference reactant state, right? So now we see that for that reference state, this is significantly, so this functional value is significantly higher than the functional value for the probability density of fully interacting system. Now we can compute the contribution to difference in activation free energy using this logarithmic formula. Okay, and this gives the result of 88 millieV, which together with 36 millieV due to reversible work fully explains the difference between molecular dynamics and static approaches. So we see, not surprisingly, that the main contribution was really due to behavior of free reactant state, which was not represented well by the static approach. And this is my final slide. Here I briefly compare the CPU time needed to complete static approach and molecular dynamics approach calculation of activation free energy. Looking at the total numbers, you see that the simulation time that we need in molecular dynamics approach is 2 orders of magnitude greater than that for static approach. So indeed, molecular dynamics calculations are very expensive. Right? That's why we are so much excited about all development in the machine learning force fields technology, especially the developments, implementation of that into VASP. With that, we should be able, in principle, to accelerate the transition state-based molecular dynamics simulations by orders of magnitude, making them as fast as static approach simulations are today. But not only that, we should, in principle, be able to go beyond transition state theory. In our calculations, we should be able to perform also those types of simulations which were not affordable when using ab initio or the DFT framework. So we should be able to access transmission coefficients or be able to routinely perform transition path sampling simulations and things like that. Unfortunately, preparation of machine-learned force fields of sufficient quality to study chemical kinetics is very challenging. And it's obvious why, because we need to prepare the force field, which represents with sufficient accuracy not only the reactant state, but also the states on the transition region. And this is very tricky because then we cannot use the usual training protocols that we can use when we just are representing the stable states. Okay, so this is quite difficult problem, and it will be addressed in the lecture by Ferenc Karsai. Thank you for your attention.
So thank you very much for the lecture, Thomas. We're going to take a 10 to 15 minute break. So thank you everyone for attending.